I would like to give this use case here. It is of a large base metal concentrator. Of course, the approach holds for metals and minerals, but I just wanted to have something very specific. The recent study of us partnering with a base metal concentrator, implementing a virtual processing expert for them, just resulted in 60 million Australian dollars additional EBIT. Due to what? What happened? The recovery has increased by 6% points. But recovery is not the only thing, right? We want to make sure that we are not losing on the throughput, and we are ultimately generating 23% more of valuable metal and concentrate versus the baseline. Just to illustrate what am I talking about and what are the scales of the projects. The plant has struggled with declining performance over the last 12 months. They had some issues with stockpile blending, but the biggest issue was processing yield and output grade. The light gray bars is the baseline, so the turquoise, or in this case greenish bars, is the engagement, really proving value and implementing the value. But the most important are these dark gray bars. It is what happened when the team was, there were no consultants on the ground, no data scientists on the ground. The team of the processing team has been doing it themselves. This is what we say the results are implemented and secured because just implemented the new way of operating has become a new operating practice. So how do we do it? It's just a schematic illustration of what actually the machine learning does. On the left-hand side, you see all the parameters that you're measuring. So there will be hundreds of tags stored in your historian systems or automation systems, if any. There will be data from lab assays about your incoming ore properties and compositions. There will be some calculated properties, obviously mass balance equations and the financial reporting. But this is the data. So there will be hundreds of tags altogether. What we really care about are the outputs, the critical outputs. The number one is profit, obviously, right? This is what we want to optimize for. We say that every plant with their very specific configuration, emission targets, production targets, has these optimal trade-offs of the output parameters that maximize profit and sustainability. So we start with the profit, then there will be the total concentrate, the valuable metal in concentrate, recovery that we get, and recovery variability. In the first step, we run predictive models. We call them prescriptive models, by the way, to first go and identify which parameters and in which relations are influencing our key outputs. Why prescriptive? Because it's not enough for me to predict then about in 6 to 8 hours from now, this shift will go off, we will not reach our production target. We want to know, is there anything we can do at this moment now without waiting for 6 to 12 hours to improve the output? So once we build a model and we deliver the model which has this tag drivers and their combinations, we first say, does it confirm reality? And once we have done it, we can go and then implement the model and reverse engineer it to tell us what exactly some changeable input parameters should be to impact the output. The benefit of predictive modeling is that even if you have a very complex process with very long residence times, you can still go and once you have a model, the model will predict and evaluate you from inputs to outputs and from outputs to inputs that momentarily in real time. This is a simple graph of some inputs of the flotation circuit, which we represent every time we notice a change in a set point, we draw a plus sign. So you see this period is 6 months of data, and plus signs indicate when the set points were being changed. And what you can see here, even visually, you don't need to be a data scientist to observe that there is not much really systematism in how different very similar set points, reagent additions or aerations are being changed. Some are changed very often, some very rarely, and again, different teams are doing different things. What we often see is that what we call maybe over-control. Sometimes, in the attempt to stabilize the circuit, operators cause high variability in the circuit. And very often, one of the insights is just do not touch it very often. The second insight is less is more. So if we really try to optimize the circuit for profit, right? It's a combination of we increase valuable metal, increase recovery. Very often the optimal solutions that improve recovery also imply less reagents use. And one of the insights we see is that lack of transparency on the costs when we're managing the circuit also sometimes counteracts the profits. So people may be using too much of reagents. Then how can we use machine learning to work for us every minute of every day? Everybody knows that the head grade, the quality and the composition of ore is the most important influencer of the results. However, what we observe and discover that the importance of the head grade is not 100%, but it's only, so in this illustration, it's 39%. The second parameter is the throughput, right? How much value through we do, and throughput, which is related to grind size. So the throughput rate, the SAG mill rate, is only responsible for 20-21% of variability in the output, which gives us our opportunity. And the opportunity here is, in this example, that if head grade and throughput are responsible for 60%, there is 40% opportunity of variability that set points on the flotation circuit are impacting the outputs. And set points we can change. We assume we can change them easier than the head grade, which can also be changed, right, by blending, and the throughput. Coming back to the example, we have improved, and you see that everything is changing all the time. This is how the feed grade has been changing, something that we couldn't control, but over like the 4 months, 1 month before the engagement and over the months of the engagement, the distributions have been changing. The direction of change for the throughput rate. So the plant has suffered earlier from attempts to increase the throughput, but as a consequence suffered from maintenance issues and also high variability. So the throughput rate has been stabilized versus the baseline. Once we have shown the model and the insights and clicked this button to say, okay, our model says that these are the optimal parameters, what did we hear from the processing team? We'll never run our plant like this. No, it's not possible. And the question is, how do you go from we will never run our plant like this to running the plant like this? This is behavioral change, and this roots in developing trust. If operators, not just technologists and metallurgists, if operators do not believe in it, it's never going to fly.